IP is a connectionless and unreliable protocol. IP packets may be delivered out of order or may cause congestion in the network. Therefore, we need to pair IP with a reliable protocol like TCP. In today's video, we'll discuss the IP datagram format. Any IP packet consists of two parts, a header and a data. If you take any IP packet, it will consist of exactly two parts. The first part is the header and the next part is the data. The header may range from 20 bytes to 60 bytes, whereas the data may range from 20 bytes to 65,535 bytes. From this diagram, we can understand that IP datagram packets are variable in length. Now what happens is, this data that has to be transmitted is paired with the header part. The header part, the IP datagram header part, consists of a number of fields. In this video, we will take up each of those fields one by one. So this header part consists of 6 logical rows. The first row may be thought of as being made up of the following fields. This is the header format and I'm talking about the first row. The first row may be thought of as made up of the following fields. The first field is the version number consisting of exactly 4 bits. So if we are using IPv4, then version will take on a value of 0100, which is the binary equivalent of 4. If you are using IPv6, then version field will take up a value of 0110, which is the binary equivalent of 6. The next field that we have is the header length field. The HLEN field also consists of 4 bits and it defines the header length. We saw in the previous diagram that the header length is variable in size. It ranges from 20 bytes to 60 bytes. Now you might be wondering, how can we define a range of 20 bytes to 60 bytes with 4 bits? The thing is, the minimum number of bits that a header length can take or the header field can take is 20 bytes. Now since it's 20 bytes, what we can do is we can encode this header length field in terms of 4-byte words. We can encode the header length field in terms of 4-byte words. What does this mean? Let's say we have a bit pattern of 0110 for header length. Then what we'll do is we'll take this binary pattern, we'll convert it into the decimal equivalent, which happens to be 6, and then we'll multiply it by 4 to get 24. This is the actual header length. That is what you mean by 4-byte words. You have to multiply the header length field by 4 in order to get the actual length of the IP datagram header field. The next field is called the service type field. The service type field, mind you, consists of 8 bits. And there is another field called the total length field. The total length field, which is made up of exactly 16 bits. Now coming to the service type field first. See, the service type field defines how the IP datagram should be handled. It means that if you take the service type field, it consists of 8 bits, right? 5, 6, 7, 8. Out of these 8 bits, now this is what? This is my MSB and this is my LSB. The least significant 2 bits, that means these 2 bits, they are unused. The remaining 6 bits are used. How are the remaining 6 bits used? The remaining 6 bits are used in the following way. The first 6 bits, that means these 6 bits from the MSB, they act as the quote point subfield. See, these 6 bits act as quote point subfield. These 6 bits act as quote point subfield. Now the quote point subfield is used in one of the two ways. If the rightmost 3 bits, if the rightmost 3 bits happen to be all zeros, then the remaining 3 bits will define priority of the datagram packet that is being transmitted. And if these 3 bits do not happen to be 0, if these 3 bits do not happen to be all zeros, then what we have is, we have a particular format which is used. If these 3 bits are all zeros, then the remaining 3 bits define the priority. And if these 3 bits are not 0, then these 3 bits define a particular format. What is the format? The format is something like this. I'm considering only the 6 bits, mind you, because the last 2 bits are unused. So if we have the last bit, the 6th bit as 0, then it defines an internet application. If we have 1 0, then it defines a local application, and if we have 1 1, then it defines an experimental application. Okay, and what about the last field? The last field, the total length field, defines the total length of the datagram. So what can be the total length? The total length of the datagram will be, since it is of 16 bits, the total length will be 2 to the power 16 minus 1, for obvious reasons. Because see, if you have 2 bits, if I have 2 bits, what are my possible combinations? 0 0, 0 1, 1 0, 1 1. In these 4 combinations, which is the value that is the largest? This one, right? This is 3. And how can you represent 3? You can represent 3 as 2 to the power of 2 minus 1, where 2 happens to be the number of bits that I've used to represent all these combinations. Similarly, if I have 16 bits as my total length, the maximum number that I can define is 2 to the power of 16 minus 1. That means the total length can at max be 2 to the power of 16 minus 1, which is 65,535. So the maximum length of the IP datagram can be 65,535. Now why will we use this total length field? This total length field is generally used to find the data length. That means we can define, see, we have the header length, we have the total length. Now how can we find the data? The data is found by subtracting the header length from the total length. If you subtract the header length from the total length, what you get is the data part, the length of the data. Okay, so this was the first row in the IP datagram field. Now let's take up the second row in the IP header field. Okay, let's see what the second row tells us. So I'm erasing all this. I hope you have noted it down. Now the second row in the IP datagram field, as I'll be showing you now, is used only for fragmentation purpose. The second row, all the fields that we'll see, there are 3 fields in total. All these 3 fields are used for fragmentation. See, the first field, there are 3 fields, right? The first field is the identification field. The first field is the identification field, and it consists of 16 bits. The next 3 bits together make up the flag bits. So we have 3 bits of flag, and the last one is the fragmentation offset. That means how far within the fragmented part have you reached. The fragmentation offset will take up 13 bits. The fragmentation offset will take up 13 bits. Remember, all these three fields, this entire row is used for fragmentation. What is fragmentation and what is segmentation? I'll defer that discussion for another video. Just keep in mind for now that the second row is used completely for fragmentation. Now coming to the third row of the IP datagram field, the third row is very interesting. The fields that are present in the third row are very useful for the transmission process. Let's see what the third row fields are made up of. See, the third row, the first field is the TTL field, time to live, and this consists of exactly 8 bits. This consists of exactly 8 bits. The next field is the protocol field. The next field is the protocol field, and the last field is the header checksum field, which is made up of 16 bits. See, now let's try to understand what the TTL field refers to. See, TTL field, the TTL field, it is used for calculating the maximum number of hops. It is used for calculating the maximum number of hops a packet can take since it has a limited lifetime. Let's try to understand this. Let's say I have a network set up like this. So I have a workstation which is connected to a router, let's call it R1, which is further connected to another router, R2, connected to another router, R3, and which is connected to another workstation. Let's call this workstation R, and let's call this workstation S. Now let's say S decides to send a packet to R. So this is the packet that S wants to send to R. Now let's say S is using IP protocol. That means it is trying to send this packet, which is an IP packet, IP datagram packet, to R. Now this packet, as we can see, since it is following the IP protocol, it will have a header part. The header part will contain this field called TTL. Now the TTL field will define the maximum number of hops that this packet can take. Let's say this packet has a TTL value of 3. Then how will this packet transmission take place? See, what will happen is this packet will first go from S to router R1. Once the packet moves from S to R1, the TTL value will be decremented by 1. So now the TTL value becomes 2. Remember, every packet will have two fields. Every packet will have two fields which we'll be seeing in the next rows. One is called the source address and the other is called the destination address. Source address is the field containing the address of the host which started the transmission process. Destination address field contains the address of the destination host to whom this packet is intended. That means here in the source address part we will have the address of S, and in the destination address field we'll have the address of R. Whenever the packet will make a hop from S to R1, the TTL count will be decremented by 1. Along with that, this destination address which is present in this packet will be checked against the address of R1. If there is a match, then R1 will consume the packet because it was intended for it, right? And if it doesn't match, if the destination address that is present in the packet doesn't match with the address of R1, then what will happen is the packet will be forwarded. So here the destination address is same as that of this workstation R. As a result, R1 router will not consume this packet. Instead, it will forward the packet to R2. Now once it forwards the packet to R2, what happens is the TTL field is decremented by 1. Again, the same process is repeated at R2. the destination address doesn't match, and the TTL value is still non-zero. Now let's see what happens when R2 forwards the packet to R3. When R2 forwards the packet to R3, the TTL field now becomes 0, and the destination address present in this packet doesn't match with the address of R3. And since the time to live of the packet has expired, see, this denotes the number of hops, the maximum number of hops that this packet can take. Why do you define such an upper limit? You define such an upper limit so that a packet doesn't fall into an infinite loop. Since it has reached R3, its TTL value has now become 0. That means it cannot make any further hop. The destination address doesn't match with the address of R3. As a result, this packet is discarded. Now, since this packet is discarded, what will happen is the sender, that means S, will be made known if IP is used in conjunction with a reliable protocol, let's say like TCP, then S is made known of this failure so that it can proceed with a retransmission of the same packet. Now, what about the protocol field? The protocol field will define the final destination protocol to which the IP datagram should be delivered. The protocol field defines the final destination protocol to which this IP datagram packet should be delivered. Now, some of the common values that are known for this protocol field. See, this protocol field has some well-known values. A value of 1 would mean, if I am not mistaken, let me just check, 1 would mean the protocol ICMP, Internet Control Message Protocol. A value of 2 would refer to the protocol IGMP. A value of 6 would refer to the protocol TCP, and a value of 17 would refer to a protocol UDP. So depending on the value, depending on one of these values, it will denote the intended protocol at the receiver end, right? It will denote the protocol which is present at the receiver end so that the transmission process can be carried out successfully. Now, why do we use the header checksum? We use the header checksum in order to aid in the error detection process. That means if you are trying to send a packet and during the transmission process, if one of the bits in the packet flipped, that means if one of the bits changed, so there is an error in the packet, and that error can be made known using one of the error detection techniques called checksum. We can take up checksum in a separate video where we can discuss the different error detection techniques. Now, moving on to the fourth row. The fourth row as well as the fifth row, I'll discuss the fourth row and the fifth row in conjunction. So the fourth row refers to the source address. The fourth row refers to the source address, and this is of 32 bits. So the source address is the address of the sending host which is trying to send a packet. As I mentioned just a while back, that every packet that is destined for transmission will have two parts. The packet will have a source address part and a destination address part. The source address is the address of the host which initiated the transmission process. The destination address is the address of the host to which the transmission is intended. So the fourth row defines the source address, and the fifth row defines the destination address. There's not much more that I can talk about these two fields. They are pretty self-explanatory in their names itself. Now moving on to the sixth row. The sixth row is called the options field. The sixth row is my options field. And it consists of anything between 0 to 40 bytes, mind you, it's bytes in this case. So it consists anywhere between 0 to 40 bytes. Now why do you use this field? You use this field if you need extra bits for the padding procedure. Sometimes it may happen that you are trying to transmit a particular packet and it needs to have a fixed length. Let's say you're trying to transmit using the Ethernet standard. So the minimum frame length for Ethernet is 64 bytes. Now let's say the packet that you have built up is 60 bytes. So you're falling short by 4 bytes. Now how can you make up these 4 bytes? You can make up these 4 bytes from this options field. What you can do is you can go for 4 bytes of padding 4 bytes of padding zeros. Then what will happen is you will be able to conform with the Ethernet standard and the transmission process can proceed successfully. Okay, so this was all about the IP datagram format. I hope you understood. If you have any doubts, you can leave a comment in the section given below. What I'll do is, in the next video, I'll take up a few numericals where I'll be discussing a few examples or few applications on the way that data can be interpreted in an IP datagram format. I hope this helps. Thank you.